4.37 light-years. At first, the number sounds almost comforting. 4.37. It is small enough to say in a single breath, small enough to write on a piece of paper without covering the page. And when astronomers tell us that Alpha Centauri is our nearest neighboring star system, the distance can almost sound like an invitation. Just 437 light-years away. You might imagine a spacecraft leaving Earth, crossing the darkness, and arriving at another star in some distant but still imaginable future. But there is a problem. A light-year is not a measure of time. It is a measure of distance. And once we translate those 4.37 light-years into kilometers, the apparent closeness disappears almost instantly. Because between Earth and Alpha Centauri lies a distance so enormous that even our fastest human-made spacecraft would need thousands of years to cross it. So tonight, we are going to take that deceptively small number, 437, and stretch it across the real scale of the universe. We will ask what it actually means to travel to another star. How fast would a spacecraft need to move? How long would the journey take? And if we launched that spacecraft today, who would still be alive when it finally arrived? Before we begin, subscribe to the channel if you want more deep space documentaries like this. And tell us in the comments where in the world you are watching from. Because wherever you are listening from tonight, the nearest star beyond our own solar system is already waiting in the same darkness above you. Its name is Alpha Centauri. But there is an important detail. Alpha Centauri is not actually one star. It is a star system. Two stars, Alpha Centauri A and Alpha Centauri B, orbit one another as a binary pair. And farther away, but still gravitationally associated with the system, is Proxima Centauri. Proxima is slightly closer to the Sun than Alpha Centauri A and B, making it the closest individual star to our solar system. For simplicity, astronomers often describe the Alpha Centauri system as being about 4.37 light-years away. That number has become famous. But what exactly is a light-year? The name creates confusion because it contains the word year. A light-year is not a duration. It is the distance light travels through vacuum in 1 year, and light moves at approximately 299,792 kilometers per second. That is so fast that in a single second, light could circle Earth roughly 7.5 times. In 1 minute, it could travel nearly 18 million kilometers. In just over 8 minutes, sunlight reaches Earth. That is the scale of speed we are dealing with. Now let light travel for an entire year. It covers approximately 9.46 trillion kilometers. That is 1 light-year. Now multiply it by 4.37. The result is more than 41 trillion kilometers. More than 41,000 kilometers. And suddenly, Alpha Centauri no longer sounds close. It sounds impossibly distant. To understand how extreme that number is, bring the scale back to our own solar system. Earth orbits the Sun at an average distance of about 150 million kilometers. That distance is 1 astronomical unit, or 1 AU. Light crosses 1 AU in roughly 8 minutes and 20 seconds. So if you could somehow stretch the Earth-Sun distance into a measuring stick, you would need more than 270,000 of those distances placed end to end to reach Alpha Centauri. Think about that. The distance that separates Earth from the Sun. The enormous emptiness astronauts experience when traveling between worlds is only a tiny fraction of the distance separating our solar system from the nearest neighboring stars. And even the size of our solar system itself becomes difficult to define. If you measure the solar system by the planets, Neptune orbits roughly 30 astronomical from the Sun, 30 Earth-Sun distances. But the heliosphere extends much farther, and the distant Oort cloud may extend thousands, perhaps tens of thousands, of astronomical units outward. Yet even those enormous distances remain tiny compared with the gap between stars. This is the first great deception of interstellar travel. On astronomical maps, stars appear close together. Look at the night sky, and you see thousands of points of light scattered across a dark background. Some appear almost adjacent. Two stars may sit only a few degrees apart in the sky. But angular proximity does not mean physical proximity. One star may be tens of light years away. Another may be hundreds. They only appear close because we are looking at them from one particular location. Space itself is mostly empty, and that emptiness is what makes interstellar travel so difficult. There is no road between stars, no chain of planets, no convenient sequence of stepping stones. There is simply a vast ocean of space. Imagine leaving Earth aboard the fastest spacecraft humanity has ever built. The spacecraft accelerates away from the Sun. Earth shrinks behind you. The planets become distant points. Eventually, even the Sun itself becomes another bright star in the background. You continue accelerating, but Alpha Centauri barely appears to move. This is one of the most counterintuitive aspects of cosmic distance. The target can be visible, and yet almost unreachable. Our fastest spacecraft have achieved extraordinary velocities. The Parker Solar Probe, for example, has reached speeds of hundreds of thousands of kilometers per hour relative to the Sun during its close solar passes. That is astonishingly fast. But even at such speeds, Alpha Centauri remains extraordinarily far away. At a speed of roughly 700,000 kilometers per hour, a simple calculation places the journey at several thousand years. Not several decades, not a few centuries, thousands of years. And that calculation assumes the spacecraft could maintain such a speed continuously along a suitable trajectory. Real missions are much more complicated. Acceleration takes time. Navigation matters. Fuel matters. The spacecraft must survive radiation. Its electronics must function for centuries. And if humans are aboard, the problem becomes almost unimaginably harder. A crew cannot simply remain alive for thousands of years waiting for a destination. Even if we solved the propulsion problem, we would still face biology. Human bodies age, generations change, civilizations transform, languages evolve, political systems disappear, technologies become obsolete. A spacecraft launched today might arrive at Alpha Centauri in a future where the world that built it no longer resembles our own. This is why interstellar travel is not merely an engineering problem. It is a problem of time. Imagine launching a spacecraft toward Alpha Centauri today. Who presses the final command? Perhaps someone alive right now. Who receives the first signal when the spacecraft arrives? Perhaps no one who witnessed its launch. If the journey lasted 100 years, an entirely different generation would be waiting. If it lasted 1,000 years, the descendants of those who launched it would be receiving the message. If it lasted 10,000 years, entire civilizations could rise and disappear during the journey. And yet, the spacecraft would still be moving toward the same star. That is the strange relationship between human time and cosmic distance. Our lives are measured in decades. Civilizations can survive for centuries. Geological processes unfold across millions of years. Stars live for millions or billions. Interstellar distances belong to the time scale of stars. Humanity is trying to cross them using technology designed within the span of a few generations. The mismatch is enormous. And yet, there is something important about the number 4.37. It is not impossibly large by the standards of the universe. In fact, on a galactic scale, Alpha Centauri is extraordinarily close. The Milky Way is roughly 100,000 light-years across. Our nearest neighboring star system is only about 4 light-years away. Compared with the width of the galaxy, Alpha Centauri is practically next door. But next door in astronomy is a dangerous phrase, because the galaxy measures distance in light years, while human civilization still measures meaningful journeys in years, decades, and lifetimes. That difference is the heart of the problem. Light crosses the distance in just over 4 years. Radio signals take the same amount of time. If we sent a message to a civilization near Alpha Centauri, we would wait more than 4 years for the message to arrive. If they replied immediately, another 4 years would pass before the response reached Earth. A simple conversation would take almost 9 years. And that is communication. Travel is vastly harder. A spacecraft cannot simply become light. According to our current understanding of physics, an object with mass cannot accelerate to the speed of light. As its velocity approaches light speed, the energy required rises dramatically. Reaching the speed of light would require an effectively infinite amount of energy under special relativity. So the universe gives us a cruel asymmetry. It allows light to cross the distance between stars in a few years. But it does not give human spacecraft the same privilege. That leaves us with an extraordinary question. If the nearest star is already more than 40 trillion kilometers away, what kind of technology would humanity need to cross that distance within a human lifetime? Would chemical rockets ever be enough? Could nuclear propulsion change the equation? Could enormous laser arrays push tiny spacecraft to a significant fraction of the speed of light? Could future civilizations build generation ships whose passengers never see Earth again? Or will interstellar travel always remain something that belongs to machines rather than humans? These questions will guide the journey ahead, because Alpha Centauri is not merely a destination. It is a test of propulsion, a test of engineering, a test of human patience, and perhaps, eventually, a test of whether our species can learn to think in timescales far beyond a single lifetime. Tonight, 437 light-years sounds small, but translated into the language of human technology, it becomes something else entirely. A distance measured in tens of trillions of kilometers. A journey potentially lasting thousands of years. A destination so close on the galactic map, and yet so far beyond the reach of today's spacecraft. And this is only the beginning. because before we can ask how to reach Alpha Centauri, we need to understand what we are actually trying to reach. 3 stars, a complex gravitational system, and at least one world that has already captured the imagination of astronomers searching for planets beyond our own. The nearest star system may be close by cosmic standards. But what is waiting there could change the way we think about our place in the galaxy. There is a deceptively simple equation at the heart of every interstellar journey. Distance divided by speed equals time. It is the kind of equation students learn in school. If you know how far away something is and how fast you can travel, you can calculate how long the journey will take. For a trip across a city, it is straightforward. For a flight between continents, it is straightforward. But apply the same equation to another star, and suddenly the simplicity disappears. Alpha Centauri is approximately 4.37 light-years away. If, somehow, spacecraft could travel at exactly the speed of light, then from Earth's frame of reference, the journey would take approximately 4.37 years. That sounds remarkably reasonable. Leave Earth today. Wait a little more than 4 years. Arrive at another star. But there is a problem. A spacecraft is not light. It has mass. And according to our current understanding of physics, an object with mass cannot be accelerated to the speed of light. The reason comes directly from Einstein's theory of special relativity. As an object with mass accelerates toward the speed of light, the energy required to continue increasing its velocity rises dramatically. The closer the object gets to light speed, the harder every additional fraction of speed becomes. At exactly the speed of light, the required energy would effectively become infinite. So the universe does not simply ask us to build a better engine. It imposes a fundamental physical limit. Light can travel at light speed. A spacecraft cannot. And that single fact changes the entire problem of reaching Alpha Centauri. So what happens if we use something humanity has actually built? To answer that, we need to look at one of the fastest human-made objects ever created, the Parker Solar Probe. Launched in 2018, Parker Solar Probe was designed to study the Sun by flying extraordinarily close to it. Its mission required something unusual. Rather than simply accelerating away from the Sun, the spacecraft repeatedly dives deep into the Sun's gravitational environment. As it moves closer to the Sun, gravity accelerates the spacecraft to extraordinary speeds. During its closest solar encounters, Parker Solar Probe reaches velocities of roughly 690,000 kilometers per hour, or around 190 kilometers per second, relative to the Sun. That is astonishing. At such a speed, you could travel around Earth several times in a single hour. You could cross the distance from Earth to the Moon in less than an hour. By human standards, it is incredibly fast. Now imagine pointing that spacecraft toward Alpha Centauri. The arithmetic is brutal. Alpha Centauri is more than 41 trillion kilometers away. Divide that distance by roughly 690,000 kilometers per hour. The result is approximately 60 million hours. Convert that into years, and the journey becomes roughly 7,000 years. 7,000. Not 7, not 7, not 70, not 700. Approximately 7,000 years. And even that number needs a major qualification. Parker Solar Probe does not simply travel through space at its maximum speed in a straight line. Its extraordinary velocity is achieved during close approaches to the Sun. That speed is part of a carefully designed orbital trajectory. The spacecraft is falling deep into the Sun's gravitational well. Its maximum velocity is therefore not equivalent to a practical interstellar cruising speed. This distinction is essential. A record speed is not automatically a useful travel speed. Imagine a race car that can reach an enormous speed for a few seconds while descending a steep hill. That does not mean it can maintain that velocity across an entire continent. The same principle applies to spacecraft. Parker Solar Probe's speed record is extraordinary, but it does not mean we can simply launch a spacecraft toward Alpha Centauri and expect it to cruise at that speed for thousands of years. An interstellar spacecraft would need a completely different mission architecture. First, it would have to accelerate, and acceleration requires energy. The spacecraft would need to increase its velocity from near zero relative to Earth or the Sun to an enormous cruising speed. The faster we want it to go, the more difficult that becomes. Then it would need to maintain that speed. That introduces another problem. Any propulsion system that provides continuous accelerations requires propellant, energy, or both. Traditional chemical rockets carry their fuel and oxidizer with them. That is practical for reaching orbit. It is practical for sending spacecraft toward other planets. But interstellar travel is another category entirely. The amount of energy required to accelerate a spacecraft to a significant fraction of light speed becomes enormous. And if the spacecraft carries the fuel needed to provide that acceleration, the fuel itself adds mass. More mass requires more energy. More energy often requires more fuel. More fuel adds more mass. The problem can become self-defeating. This is one reason rocket scientists are interested in propulsion systems that do not require carrying all of their energy on board. Concepts such as laser sails. Imagine using enormous laser arrays to push extremely lightweight spacecraft. The laser remains behind. The spacecraft carries a reflective sail. Photons strike the sail and transfer momentum. Individually, each photon provides an incredibly tiny push. But an enormous number of photons, acting continuously over a long period, could potentially accelerate a very small spacecraft to a substantial fraction of the speed of light. This is the basic idea behind concepts such as breakthrough starshot. The proposed spacecraft would not look like the massive robotic probes we currently send to the outer planets. They would be tiny, extremely lightweight, more like miniature electronic sails than traditional spacecraft. The reason is simple. At relativistic speeds, mass becomes the enemy. Every additional kilogram makes acceleration more difficult. And that brings us to another critical distinction. The journey to Alpha Centauri is not just about reaching a high speed. It is about reaching a high speed efficiently. Suppose we somehow accelerate a spacecraft to 10% of the speed of light. That is roughly 30,000 kilometers per second. At that velocity, Alpha Centauri could theoretically be reached in roughly 44 years, ignoring acceleration and deceleration. Now imagine 20% of light speed. The travel time falls to roughly 22 years. At 50% of light speed, the simple Earth frame calculation would be less than 9 years. Suddenly, interstellar travel begins to look like something that could fit within a human lifetime. But the engineering challenge becomes dramatically harder as the velocity rises. And there is another problem that simple travel time calculations hide. You have to stop. A spacecraft traveling at 20% of the speed of light may reach Alpha Centauri after a few decades. But if it simply flies past the system at that velocity, it has very little time to investigate anything. To enter orbit around another star or planet, it must remove an enormous amount of kinetic energy. In other words, the spacecraft must accelerate it, cruise, and then decelerate. Every one of those phases requires energy. For a mission carrying humans, the requirements become even more severe. The spacecraft must protect its crew from radiation. It must recycle air and water. It must provide food. It must control temperature. It must survive for decades. And it must remain reliable despite having no possibility of repair by humans. The engineering problem expands from propulsion into life support, materials science, navigation, communications, and long-term reliability. Even an unmanned probe faces serious challenges. At interstellar velocities, microscopic particles become dangerous. A grain of dust that would be harmless at ordinary spacecraft speeds can carry enormous kinetic energy when encountered at a significant fraction of the speed of light. The interstellar medium itself becomes an obstacle. Hydrogen atoms become projectiles. Dust becomes a threat. Radiation becomes more severe. The spacecraft must survive not only the journey, but the physics of moving through the journey at extreme speed. Then there is navigation. Alpha Centauri is not sitting still waiting for us. The entire star system is moving through the Milky Way. The Sun is moving. Earth is moving. The target is moving. A spacecraft launched today will arrive decades or centuries later, when Alpha Centauri will occupy a slightly different position relative to our solar system. Interstellar navigation, therefore, requires predicting trajectories across enormous distances and enormous periods of time. A tiny error at the beginning can become a huge miss at the destination. This is another reason interstellar travel is fundamentally different from traveling to the Moon or even Mars. The distances are so large that small errors accumulate. The spacecraft cannot simply make a quick correction when it gets close. There may be no fuel available for a major correction, and communication delays mean Earth cannot react instantaneously. At Alpha Centauri, a command from Earth would take more than 4 years to arrive. Any response would take another 4 years. That means a spacecraft operating there would need a high degree of autonomy. It would have to make decisions without waiting for Earth. So the equation we started with, distance divided by speed equals time, is correct, but it is incomplete. The real equation for interstellar travel includes acceleration, propellant, energy, navigation, shielding, communications, deceleration, reliability, and time. Lots of time. At ordinary spacecraft velocities, the journey is measured in thousands of years. At a significant fraction of light speed, it could fall to decades. But getting to those velocities may require technologies that do not yet exist at the necessary scale. And this is where the story moves beyond astronomy. We already know where Alpha Centauri is. We already know approximately how far away it is. We can measure its motion. We can study its stars. We can search for planets. The problem is no longer discovering the destination. The problem is crossing the distance. And that is one of the most profound technological challenges humanity has ever considered. Because the universe has given us something extraordinary. A nearby star system. Only 4.37 light-years away. Close enough that light can cross the gap within a human lifetime. Close enough that we can detect its stars from Earth. Close enough that future telescopes may reveal more about the worlds orbiting within it. And yet, using propulsion technology we currently possess, it remains effectively unreachable on human timescales. The contradiction is extraordinary, cosmically close, technologically distant. But perhaps we do not need to make the spacecraft enormous. Perhaps we need to make them incredibly small. Perhaps the future of interstellar travel will not begin with a giant starship carrying hundreds of people. Perhaps it will begin with something weighing only a few grams, pushed by a beam of light, accelerating across the darkness at a speed no conventional rocket could ever achieve. And if that sounds like science fiction, the physics behind the concept already exists. The question is whether humanity can engineer it. Because the journey to Alpha Centauri may not require us to break the laws of physics. It may require us to understand those laws well enough to finally work with them. And that changes the question. We are no longer asking whether another star is far away. We already know it is. We are asking something much more difficult. How much energy are we willing to spend to make the distance smaller? Not physically, but in time. Because somewhere beyond those 41 trillion kilometers, Alpha Centauri continues moving through the Milky Way. And if humanity ever intends to reach it, the first challenge will not be finding the star. It will be building a machine capable of surviving the journey. A rocket can be incredibly fast and still be almost useless for interstellar travel. That sounds contradictory. Modern rockets can launch hundreds of tons from Earth's surface. They can accelerate spacecraft to enormous velocities. They can send probes across the solar system. They can reach the moon. They can reach Mars. They can fly past Jupiter and Saturn. And some spacecraft have reached speeds that would be unimaginable to anyone living just a few centuries ago. But when the destination is another star, those achievements suddenly look very different. Because the problem is not simply getting fast. The problem is getting fast enough. And that is where chemical propulsion begins to reveal its fundamental limitation. A chemical rocket works through one of the oldest principles in physics: conservation of momentum. The rocket pushes mass backward. The rocket itself moves forward. It does not need air to push against. This is why rockets work in space. A jet engine needs atmospheric oxygen. A propeller needs surrounding material to push against. A rocket carries what it needs on board: fuel, oxidizer, combustion chamber, nozzle. The fuel and oxidizer react. The chemical energy stored in their molecular bonds is released as heat. The resulting gases become extremely hot and expand rapidly. The nozzle directs those gases backward at high velocity, and the spacecraft accelerates in the opposite direction. It is a remarkably elegant system. Burn fuel, throw mass backward, move forward, but there is a catch. The rocket has to carry the mass it is going to throw away. And that creates one of the most unforgiving equations in aerospace engineering. The rocket equation. Its basic form is delta V Vn m0 mef, the change in velocity. Ve is the effective exhaust velocity. m0 is the initial mass. Mf is the final mass after the propellant has been consumed. At first glance, it looks like an ordinary mathematical relationship. But hidden inside that equation is a brutal reality. Velocity increases only logarithmically with mass ratio. That means adding more fuel does not produce a proportional increase in final velocity. You cannot simply say, if we need twice the speed, let's carry twice as much fuel. It does not work that way. The additional fuel has mass, and because the fuel has mass, you need additional energy to accelerate that fuel. So you need more fuel to accelerate the extra fuel, and then more fuel to accelerate that additional fuel. The equation begins eating itself. This is why rockets have multiple stages. Instead of carrying empty tanks, engines, and structural components all the way to the destination, a launch vehicle throws those components away once they are no longer needed. Stage 1 burns its propellant. Then it separates. The dead mass falls away. Stage 2 continues. Then another stage may separate. By repeatedly discarding unnecessary mass, engineers improve the effective mass ratio. This is one of the reasons modern rockets can achieve the extraordinary velocities required for planetary exploration. But even with staging, chemical propulsion has a fundamental ceiling. The limitation is the exhaust velocity. Chemical reactions simply do not release enough energy per kilogram to produce the enormous exhaust velocities needed for rapid interstellar travel. Modern chemical rocket exhaust velocities are typically measured in several kilometers per second. That is fast. But the speed of light is approximately 300,000 kilometers per second. The difference is not a matter of degree. It is a completely different regime. Imagine a spacecraft traveling at 10 kilometers per second. That is already extremely fast. Now compare it with light. Light travels 30,000 times faster. Even a spacecraft moving at 100 kilometers per second is still roughly 3,000 times slower than light. And Alpha Centauri is 37 light-years away. That is where the numbers become uncomfortable. Suppose, purely as a simplified example, that a spacecraft could cruise continuously at 10 kilometers per second, ignoring acceleration and deceleration, crossing approximately 41 trillion kilometers, would take more than 130,000 years. At 100 kilometers per second, the journey would still take more than 13,000 years. At 1,000 kilometers per second, it would still take more than 1,300 years. These are not practical chemical rocket velocities for an interstellar mission. They are simply useful reference points. They reveal the scale of the problem. Even if we could somehow make a spacecraft 10 times faster, the nearest star would still be thousands of years away. And that is the first major shock. The problem is not that our rockets are poorly designed. Our rockets are extraordinarily sophisticated. The problem is that chemical energy is simply not dense enough to accelerate a spacecraft to interstellar velocities. Consider what happens during a conventional launch. A rocket begins on Earth with an enormous amount of propellant. Most of the vehicle's initial mass may consist of fuel and oxidizer. The payload, the part we actually want to send into space, is only a fraction of the total. The rest is propulsion infrastructure, tanks, engines, structural material, fuel, oxidizer, and the rocket must accelerate all of it. Then it throws much of it away. That is already an extraordinary engineering compromise. Now imagine scaling the same concept to an interstellar mission. We want a spacecraft to leave the solar system at a significant fraction of the speed of light. The spacecraft must carry enough energy to accelerate itself. If it carries that energy as chemical fuel, the fuel itself adds mass. That extra mass requires more energy, which requires more fuel, which adds more mass. The rocket equation becomes increasingly unforgiving. And there is another problem. A chemical rocket does not just need enough energy to reach a high speed. An interstellar spacecraft may also need to slow down when it arrives. This means the mission may require two enormous propulsion budgets. One to accelerate, another to decelerate. If the spacecraft simply flies past Alpha Centauri at extreme velocity, the encounter could last only moments. For a scientific mission, that is not enough. You would want to enter the system, observe the stars, study planets, search for atmospheres, measure magnetic fields, perhaps deploy smaller probes, perhaps even enter orbit around a planet. Every one of those actions requires control over velocity. So the real mission is not get there fast. It is accelerate, survive, navigate, arrive, and stop. Chemical propulsion struggles with every part of that problem. But perhaps the most unsettling question is not whether a chemical rocket could make the journey. It is whether anything could survive it. Imagine a probe taking 10,000 years to reach Alpha Centauri. When it launches, modern civilization exists in its current form. 1,000 years later, almost everything about human society could be different. 2,000 years, 5,000, 10,000. The Roman Empire lasted only centuries. Modern industrial civilization is only a few hundred years old. Written human history itself occupies a tiny fraction of the time such a spacecraft might require. Could the electronics survive? Could the propulsion system remain functional? Could radiation slowly damage its components? Could microscopic impacts destroy its instruments? Could its software still be understood? Could anyone on Earth still be listening? These are not merely engineering questions. They are questions about civilization. A spacecraft can physically continue moving for thousands of years. That does not mean it can successfully complete a mission. Those are two completely different things. A piece of metal can orbit the galaxy for millions of years. But a scientific spacecraft requires functioning sensors, power, communications, navigation systems, and a receiving civilization capable of interpreting the data. The difference is enormous. This is why interstellar travel requires us to distinguish between survival and mission success. A spacecraft might survive the journey, but can it still operate? Can it communicate? Can it recognize its destination? Can it correct its trajectory? Can it transmit useful scientific information? And perhaps the strangest question of all, will anyone still be there to receive the message? Now return to our original number, 4.37 light years. On a galactic scale, that is almost nothing. The Milky Way is approximately 100,000 light years across. Alpha Centauri is practically our cosmic neighbor, yet chemical propulsion could turn that neighboring stvun into a destination measured in thousands or even tens of thousands of years. This is why the distance itself is not the only problem. The real problem is the mismatch between cosmic distance and human propulsion technology. The universe does not demand that we cross an enormous galaxy before reaching another star. It gives us a neighboring system only 4 and a fraction light-years away. But our technology currently moves through space at speeds that are tiny compared with the scale of light. This is similar to trying to cross an ocean using a bicycle. The ocean is not necessarily impossible to cross. The vehicle is simply wrong for the distance. And that is exactly what chemical rockets are. They are brilliant machines for the solar system. They are just not designed for the stars. Within the solar system, chemical rockets can accomplish extraordinary things. A spacecraft can launch from Earth, perform gravity assists, adjust its trajectory, visit another planet, enter orbit, land, take samples, return data. These missions can last years or decades. Chemical propulsion is incredibly effective when combined with orbital mechanics and gravity assists. But interstellar space changes the equation. There are no nearby planets waiting to provide convenient gravity assists. There is no atmospheric braking at the destination, unless a planet happens to have an atmosphere, and the spacecraft is designed to use it. There is no infrastructure waiting for us. There is simply distance. And the spacecraft must carry almost everything required for the journey. That is why engineers are exploring propulsion concepts fundamentally different from chemical rockets. Nuclear propulsion, fusion propulsion, electric propulsion, beamed energy, laser sails, antimatter concepts. Each attempts to solve the same underlying problem. How do you generate far more useful velocity without carrying an impossible amount of propellant? Some approaches improve exhaust velocity. Others separate the energy source from the spacecraft. Some attempt to use external energy, and some attempt to radically reduce the spacecraft's mass. The solution may not be one technology. It may be an entirely different philosophy of spacecraft design. Instead of building a massive vehicle and filling it with fuel, perhaps future missions will send tiny machines. Instead of carrying the energy on board, perhaps energy will be transmitted to the spacecraft from far away. Instead of accelerating for minutes, perhaps a spacecraft will accelerate continuously for hours, days, or even months. That is where the story begins to move beyond conventional rocketry. Because chemical propulsion has already taken humanity remarkably far. It carried us from Earth. It sent humans to the moon. It launched probes toward every major region of the solar system. It helped create the first machines to escape the immediate neighborhood of the sun. But when we ask chemical rockets to cross the gap between stars, they reveal their greatest weakness. They are powerful, they are reliable, they are proven, and yet they are painfully slow. The nearest star is only 4.37 light-years away. But with chemical propulsion, that small number can become a journey longer than the entire span of recorded human history. That is the real shock. Alpha Centauri is not impossibly far away, because space is too large. It is impossibly far away, because our propulsion systems are too slow. And if we want to change that equation, simply building a larger chemical rocket will not be enough. We need a fundamentally different way to move through space. Because the next step toward another star may require us to stop throwing our own fuel overboard and start using the universe itself as part of the engine. If chemical rockets are the old highway of spaceflight, then ion engines represent something very different. They are not powerful in the way a launch rocket is powerful. They do not roar. They do not produce enormous flames. They do not push a spacecraft violently away from Earth. Instead, they whisper. A tiny stream of electrically charged particles leaves the engine at extremely high velocity. The spacecraft once receives an equally tiny push in the opposite direction. At first, the acceleration is almost laughably small, but the engine can continue operating for weeks, months, sometimes years, and that changes everything. Because when we talk about spacecraft propulsion, there are two numbers that are easy to confuse: thrust and specific impulse. Thrust tells us how hard an engine pushes. Specific impulse tells us how efficiently the engine uses its propellant. A chemical rocket can produce enormous thrust. That is exactly what we need to lift a massive vehicle from Earth's surface. But the exhaust velocity of chemical propulsion is relatively limited. Ion engines reverse that trade-off. They produce very little thrust, but they can achieve extraordinarily high exhaust velocities. And that means they can extract much more velocity from each kilogram of propellant. The basic principle is surprisingly elegant. An ion engine takes a propellant, often xenon or another suitable gas, and electrically ionizes it. The atoms lose electrons. They become positively charged ions. Then powerful electric fields accelerate those ions to extremely high velocities. The ions are expelled from the spacecraft. The spacecraft moves in the opposite direction. No chemical explosion is required. No massive combustion chamber is necessary. The energy comes primarily from electricity, and because the ions can be accelerated to much higher exhaust velocities than chemical exhaust gases, the engine can achieve a much higher specific impulse. That is the great advantage. For long-duration missions, fuel efficiency matters enormously. An ion engine can use a relatively small amount of propellant to produce a large cumulative change in velocity. But there is a catch. The thrust is tiny, very tiny. A chemical launch engine may produce hundreds of thousands or even millions of newtons of thrust. An ion engine can produce only a fraction of that. The spacecraft does not leap forward. It slowly gains speed. That sounds like a weakness. But in deep space, where there is no atmospheric drag, and gravity can be carefully managed, continuous low thrust becomes extremely useful. Imagine pushing a shopping cart with one finger. The force is almost nothing. But if you could keep pushing that cart continuously for months, the final speed could become significant. That is the philosophy behind electric propulsion. Don't push hard. Push for a very long time. Space missions have already demonstrated the power of this approach. NASA's Dawn spacecraft used ion propulsion to visit the asteroids Vesta and Ceres. The engine operated for thousands of hours. Its thrust was tiny. But over time, that tiny thrust allowed the spacecraft to change its orbit dramatically. Dawn demonstrated something fundamental. A spacecraft does not always need a powerful engine. Sometimes it needs an efficient engine that can keep pushing. For missions within the solar system, this can be transformative. But then we return to Alpha Centauri, and the problem becomes much larger, much larger. An ion engine may operate for months or years, but the spacecraft still needs to accumulate enough velocity to cross more than 41 trillion kilometers. And there is another limitation. The engine requires electrical power. The more thrust we want from an electric propulsion system, the more power we need. Solar panels work wonderfully near the sun. But the farther a spacecraft travels, the weaker sunlight becomes. At Alpha Centauri's distance, solar energy from our sun is effectively negligible compared with what a spacecraft receives near Earth, Phlegon. So an interstellar ion spacecraft would need an enormous, independent power source. That brings us to nuclear energy. Unlike chemical reactions, nuclear reactions operate at vastly higher energy densities. A small amount of nuclear fuel can contain millions of times more energy per unit mass than conventional chemical fuels. That does not automatically solve interstellar travel, but it changes the physics of the problem. One of the most straightforward concepts is nuclear thermal propulsion. Instead of using a chemical reaction to heat propellant, a nuclear reactor provides the heat. The reactor can heat hydrogen to extremely high temperatures. The hot hydrogen expands through a nozzle. The basic rocket principle remains the same: throw mass backward, move forward. But because the nuclear reactor can produce much higher temperatures than a conventional chemical combustion process, the exhaust velocity can be substantially higher. That means more useful velocity from the same amount of propellant. Nuclear thermal propulsion could dramatically improve missions within the solar system. It could potentially shorten travel times to Mars. It could provide more efficient transportation for human exploration. But Alpha Centauri remains another category entirely. Even a significant improvement over chemical propulsion does not automatically turn a decades-long or centuries-long journey into a practical interstellar mission. To cross interstellar distances within a human lifetime, we need far more than incremental improvement. We need a propulsion system capable of generating enormous amounts of energy while keeping the spacecraft's mass manageable. That leads to nuclear electric propulsion. Here, the reactor generates electricity. The electricity powers an electric propulsion system. The result combines the high efficiency of ion or plasma propulsion with the continuous energy supply of a nuclear reactor. This could allow a spacecraft to operate its engines for extremely long periods without depending on sunlight. For deep space missions, that is a major advantage. But again, there is a fundamental difference between going farther in the solar system and going to another star. A nuclear electric spacecraft might reach destinations such as the outer planets more efficiently. It might operate for years. It might gradually accumulate enormous velocity compared with conventional chemical propulsion. But Alpha Centauri is still more than 4.37 light-years away. At ordinary deep space velocities, the journey remains measured in thousands of years. To reduce that to decades, we need another leap. And this is where some of the most extraordinary propulsion concepts in human history appear. In the 20th century, engineers considered an idea that sounds almost unbelievable today: Project Orion. The concept was simple in principle and extreme in execution. Instead of burning chemical fuel continuously, the spacecraft would use controlled nuclear explosions behind the vehicle. A series of nuclear detonations would produce expanding plasma, A massive pusher plate would absorb the momentum. The spacecraft would be accelerated forward. Again and again, explosion after explosion. The concept was studied seriously in the late 1950s and early 1960s. And the basic physics was not imaginary. Nuclear explosions contain enormous amounts of energy. If that energy could be converted into spacecraft momentum efficiently, a vehicle could potentially achieve velocities far beyond conventional chemical rockets. The proposed spacecraft were enormous. Not tiny probes, not conventional rockets. Massive vehicles designed around a propulsion concept completely different from anything humanity had ever flown. Project Orion demonstrated something important. When the energy source becomes sufficiently powerful, the rules of spacecraft design begin to change. But Orion also faced enormous practical, political, environmental, and engineering problems. Nuclear explosions in or near Earth's atmosphere created obvious concerns. International treaties and the political reality of nuclear weapons made the concept increasingly difficult to pursue. The project was eventually abandoned, but the underlying idea remained. If nuclear energy can provide vastly more energy than chemical combustion, perhaps it can become the foundation of true interstellar propulsion. Then came an even more ambitious concept. Project Daedalus, developed in the 1970s by the British Interplanetary Society. Daedalus explored the possibility of sending an unmanned spacecraft to another star using nuclear fusion. Fusion is fundamentally different from ordinary nuclear fission. Fission splits heavy atomic nuclei. Fusion combines light nuclei. The Sun itself is powered by fusion. Deep inside the Sun, hydrogen nuclei combine under enormous pressure and temperature, releasing energy. If humanity could reproduce controlled fusion efficiently enough, the energy density could be extraordinary. Project Daedalus imagined a spacecraft using pulsed fusion reactions to accelerate itself to a substantial fraction of the speed of light. The proposed mission was not designed for a casual trip. It was designed to reach another star. The target was Barnard's star, roughly 6 light-years away. Daedalus was a conceptual study, not a spacecraft that was built. But it demonstrated something revolutionary. With sufficiently advanced fusion propulsion, interstellar travel could potentially move from the realm of thousands of years toward the realm of decades. And suddenly, Alpha Centauri begins to look different. Not easy, not close, but perhaps physically approachable. Imagine a spacecraft traveling at 10% of the speed of light. That is approximately 30,000 kilometers per second. At that velocity, the simple travel time to Alpha Centauri would be around 44 years, ignoring acceleration and deceleration. At 20% of light speed, the simple travel time falls to roughly 22 years. That is still an extraordinary mission, but it is no longer than human civilization. It could fit within a person's lifetime. A child could watch the spacecraft launch, grow old, and perhaps still be alive when the spacecraft arrived. That is the transformative power of advanced propulsion. Not simply making a spacecraft faster, changing the relationship between distance and human time. But fusion propulsion has an enormous problem. We still do not have a mature fusion propulsion system capable of operating as a practical spacecraft engine. Producing fusion energy on Earth is already an extraordinary challenge. Producing it continuously, controlling it, making the system compact, converting the reaction energy into directed thrust, protecting the spacecraft, managing heat, carrying enough fuel, and making the entire system reliable for decades is another level of difficulty. There is also the question of fuel. Some fusion concepts require isotopes that are difficult to obtain or manage. Others produce energetic neutrons that can damage spacecraft structures and generate enormous thermal loads. And then comes the final problem. Even if we build a fusion engine capable of accelerating a spacecraft to a significant fraction of light speed, we still need to slow it down. The same enormous energy that allowed the spacecraft to accelerate must somehow be removed at the destination. Otherwise, we have built an extraordinarily expensive projectile, not an interstellar spacecraft. This is the recurring theme of propulsion. Every solution creates another problem. Chemical rockets provide high thrust but relatively low exhaust velocity. Ion engines provide extraordinary efficiency but very low thrust. Nuclear thermal systems can increase exhaust velocity but still depend on carrying propellant. Nuclear electric systems provide long-duration power but require enormous electrical systems. Nuclear pulse propulsion could provide tremendous energy but raises major practical and political challenges. Fusion propulsion could potentially reach relativistic velocities, but controlled fusion propulsion does not yet exist. So how far can we really go? With today's technology, we can travel across the solar system. With improved nuclear propulsion, we could potentially make those journeys faster. With advanced fusion systems, we might someday imagine reaching nearby stars in decades. But none of these systems currently gives humanity a practical interstellar spacecraft. And that distinction matters. The physics may permit something. The engineering may make it extraordinarily difficult. The economics may make it even harder, and civilization must still decide whether the effort is worth the cost. Alpha Centauri, therefore, sits at a fascinating boundary. It is close enough to be a realistic target for theoretical interstellar mission studies, but far enough away to expose every weakness in our current technology. The journey forces us to confront the fundamental question of propulsion. How much energy can a civilization control? Because the farther we want to travel, the more important energy becomes. And eventually, even nuclear propulsion may not be enough. There may be another possibility. Instead of carrying the engine, perhaps we could leave the engine behind. Instead of carrying the fuel, perhaps we could send energy across space. Instead of pushing a massive spacecraft, perhaps we could push something almost impossibly light. A sail, a beam of light, and a spacecraft small enough that the energy required to accelerate it becomes manageable. That idea could change the interstellar equation more dramatically than any conventional rocket. Because perhaps the fastest way to another star is not to build a bigger rocket. Perhaps it is to stop building the rocket around the fuel at all. For more than a century, the basic architecture of the rocket has remained remarkably familiar. Carry fuel, burn fuel, throw exhaust backward, move forward. The entire vehicle carries the machinery required to accelerate itself. But what if the spacecraft did not need to carry its engine? What if it did not need to carry most of its energy? What if the force pushing it forward came from somewhere else entirely? Not from a chemical reaction, not from a nuclear explosion, not from an engine mounted on the spacecraft, but from a beam of light fired from Earth. At first, the idea sounds almost absurd. How could something as intangible as light push a spacecraft? Light has no rest mass. You cannot hold a photon in your hand. You cannot pour sunlight into a fuel tank. And yet light carries something extraordinarily important: momentum. And momentum can produce force. That simple fact could eventually allow humanity to send a spacecraft toward another star without carrying its main propulsion system on board. The concept is called a light sail, or when the light source is a powerful laser array, a laser sail. The basic idea is almost beautifully simple. Take an extremely thin, highly reflective sheet. Attach an extremely lightweight spacecraft to it. Then shine an enormous laser beam onto the sail. The photons strike the reflective surface. They bounce away, and in doing so, they transfer momentum to the sail. The force from each photon is tiny, almost unimaginably tiny. But a laser beam can contain an enormous number of photons. If enough photons strike the sail at the same time, the combined force becomes measurable. And if that force acts continuously, the spacecraft accelerates. There is no propellant being thrown backward, no combustion chamber, no massive tank of fuel. The energy source remains behind. This changes the rocket equation in a profound way. Traditional spacecraft carry both the engine and the fuel needed to operate it. A laser sail can leave most of the energy source behind. The spacecraft only needs to carry the sail. The electronics, sensors, communication equipment, and whatever scientific instruments are necessary, and this creates an enormous advantage: mass. In interstellar propulsion, mass is one of the greatest enemies. Every kilogram requires more energy to accelerate. Every kilogram added to the spacecraft makes the mission harder. But if the spacecraft can be made extremely small, the energy required to accelerate it becomes dramatically smaller. That is the central idea behind one of the most ambitious interstellar concepts ever proposed: Breakthrough Starshot. The project envisions sending tiny spacecraft toward a nearby star system at a significant fraction of the speed of light. The proposed target is the Alpha Centauri system, including its nearby star, Proxima Centauri. The spacecraft would not resemble the giant starships of science fiction. They would be incredibly small. The basic concept involves miniature probes attached to ultralight sails. The probes could contain cameras, sensors, communication systems, and other miniature electronics. The goal would be to use a powerful laser array to accelerate these tiny spacecraft to roughly 20% of the speed of light. That number is extraordinary. 20% of light speed is approximately 60,000 kilometers per second. At that velocity, a spacecraft would cross the distance between Earth and the Moon in only a few seconds. It could circle Earth in a fraction of a second. And most importantly, Alpha Centauri would no longer be thousands of years away. At 20% of light speed, the simple Earth frame travel time across 37 light years is approximately 22 years. That does not mean the mission would necessarily take exactly 22 years. The spacecraft must first accelerate. The beam cannot remain perfectly aligned forever. The spacecraft must survive the journey, and the mission architecture would need to account for the exact trajectory. But the scale has changed. We have moved from thousands of years to decades. That is the revolution. Not because we have discovered a shortcut through space. The distance remains the same. But because we have found a radically different way of delivering energy to the spacecraft. The laser does the heavy lifting. Imagine a spacecraft weighing only a few grams. Now imagine a laser array capable of producing an enormous beam of concentrated energy. The beam strikes the sail. The sail accelerates. At first, the motion is almost imperceptible, then faster and faster. And because the spacecraft is so light, the acceleration can continue. The laser does not need to push it forever. It needs to push it long enough to give the spacecraft the required velocity. Then the spacecraft separates from the beam and continues coasting through interstellar space. This is fundamentally different from a rocket. A rocket carries its energy source. A laser sail receives its energy remotely. But the elegance of the idea hides some enormous engineering problems. The first is obvious. How powerful must the laser be? To accelerate a gram-scale spacecraft to a significant fraction of light speed, the laser's system must deliver an extraordinary amount of energy. The exact requirements depend on the spacecraft mass, sail design, beam duration, acceleration profile, and efficiency. But the power involved would be enormous. This would not be a laboratory laser. It would require a massive coordinated laser infrastructure. Thousands of individual emitters might need to operate together as one giant system. The array would have to maintain precise synchronization, and the energy demand would be immense. A civilization capable of building such a system would need not only advanced laser technology, but enormous electrical generation and energy storage infrastructure. Then comes another problem: the beam itself. Light naturally spreads as it travels. A laser can be highly focused, but maintaining an extremely narrow beam over astronomical distances is extraordinarily difficult. The farther the spacecraft travels, the more challenging it becomes to keep the beam concentrated on a tiny moving sail. The laser array must remain aligned with extraordinary precision. The spacecraft is accelerating. The Earth is rotating. The Earth is orbiting the Sun. The target star is moving. The laser beam itself is subject to diffraction, and the sail is tiny. A small error could mean the spacecraft moves outside the useful portion of the beam. The entire system, therefore, becomes a problem in precision optics. Then there is the sail. The sail must be extraordinarily light, but it must also be highly reflective. It needs to absorb as little laser energy as possible, because any energy absorbed becomes heat. And at enormous laser intensities, even a tiny amount of absorbed energy could destroy the material. The sail, therefore, has to balance several competing requirements: low mass, high reflectivity, high thermal resistance, mechanical strength, long-term stability, and the ability to survive the enormous acceleration produced by the laser beam. This is not ordinary materials science. It is a completely new regime. A sail designed to catch sunlight near Earth can be relatively large and delicate. A laser sail designed to reach 20% of light speed must survive a vastly more intense environment. And even if engineers solve the launch problem, the journey itself creates another threat: interstellar dust. Space looks empty, but it is not perfectly empty. Tiny grains of dust and microscopic particles exist between the stars. At ordinary spacecraft speeds, a microscopic particle may cause limited damage. At relativistic velocities, the situation changes dramatically. A tiny grain becomes a projectile carrying enormous kinetic energy at 60,000 kilometers per second. An impact that would normally be insignificant could become catastrophic. The spacecraft could encounter microscopic particles that vaporize themselves and portions of the spacecraft upon impact. Even individual atoms become relevant. Radiation becomes more complicated. The interstellar medium becomes part of the spacecraft's environment. The front surface may experience continuous bombardment from particles that the spacecraft cannot see coming. So the probe must be designed not only to accelerate rapidly, but to survive a journey at an extraordinary velocity. This creates another difficult question. What happens when the spacecraft arrives? A laser sail is excellent at accelerating a tiny probe, but deceleration is much harder. The laser that launched it remains millions or billions of kilometers behind. There is no obvious equivalent laser array waiting at Alpha Centauri. If the probe arrives at 20% of light speed, it cannot simply stop. It would race through the star system in a matter of minutes. For a flyby mission that may be acceptable, the spacecraft could take images as it passes. Its instruments could collect measurements. It could examine planets and their atmospheres if the trajectory were carefully planned. But it could not easily enter orbit. This is an important distinction. Breakthrough Starshot is primarily conceived as a flyby concept. The spacecraft would cross the target system at extraordinary speed, collect as much information as possible, and then continue into interstellar space. That creates another challenge. Communication. Imagine a probe only a few grams in mass, tens of trillions of kilometers away. It has no giant radio antenna. It has limited electrical power. It has only a tiny amount of hardware. And it must send scientific data back across more than 4 light-years. The signal will be extraordinarily weak. The receiving system on Earth would therefore need to be enormous and extremely sensitive. The spacecraft may need a highly directional laser communication system. Its position must be known precisely. The beam must be aimed back toward Earth, and the probe must somehow determine where Earth is while traveling through another star system. This becomes an extraordinary exercise in miniaturization. Every gram matters. Every watt matters. Every square centimeter of sail matters. The spacecraft cannot afford unnecessary hardware. Instead of carrying a traditional computer, it may require highly integrated electronics. Instead of a large antenna, it might use the sail itself, or a miniature optical communication system. Instead of a conventional camera, it might use tiny sensors capable of producing scientifically useful images with extremely limited resources. The spacecraft becomes less like a traditional probe and more like a microscopic technological organism. That is precisely why a gram-scale spacecraft may be more realistic for an early interstellar mission than a human starship. Sending people introduces an entirely different set of requirements: food, water, radiation protection, artificial gravity, life support, medical systems, redundancy, habitat structures, deceleration. A human spacecraft could weigh thousands or millions of kilograms. A gram-scale probe might weigh less than a paperclip. The difference is enormous. If the energy required to accelerate an object increases with its mass, then reducing mass is one of the most powerful ways to make relativistic travel more achievable. And this is the genius of the laser sail concept. It does not try to make the rocket more powerful. It tries to make the spacecraft almost weightless. But there is an important reality check. A concept being physically plausible does not mean it is technologically ready. We have not yet demonstrated a complete interstellar laser sail system. The required laser infrastructure does not currently exist at the proposed scale. The materials required for the sail remain a major research challenge. Long-range beam control is difficult. Dust impacts are a serious concern. Communication from the target system remains challenging, and the question of deceleration remains largely unresolved for a simple one-way laser launch architecture. So why take the concept seriously? Because unlike faster-than-light travel, it does not require us to break known physical laws. It uses a phenomenon we already understand. Photons carry momentum. Reflective surfaces can exchange momentum with light. Light sails have already been demonstrated in space at smaller scales. The leap is not from impossible physics to possible physics. It is from demonstrated physics to enormous engineering. And that distinction matters. Humanity does not need to invent a new law of nature to imagine reaching another star. We may simply need to build machines on a scale far beyond anything we have constructed before. A laser array, an ultralight sail, a microscopic spacecraft, a communication network capable of listening across 4 light years, and a mission designed to survive decades of isolation. If we can solve those problems, the number 4.37 changes meaning once again. At chemical rocket speeds, Alpha Centauri becomes a destination separated from us by thousands of years. With advanced nuclear propulsion, the journey could potentially be shortened dramatically. With a laser sail reaching 20% of light speed, the simple travel time falls to roughly 22 years. That is still an extraordinary journey, but it is no longer beyond the time scale of human civilization. A child could be born on Earth after launch, grow into adulthood, and potentially live to see the first data arrive from another star. For the first time, interstellar travel begins to resemble something more than a thought experiment. Not a human expedition, not yet, but perhaps a robotic messenger, a tiny machine crossing the darkness between stars. And perhaps that is how humanity's first true journey to another star will begin. Not with a giant starship, not with hundreds of astronauts, not with an engine capable of carrying its own enormous fuel supply, but with something almost absurdly small, a few grams of technology, attached to a sheet thinner than a human hair, pushed by photons from a laser array on Earth, accelerating until the spacecraft is traveling at a fraction of the speed of light. Then, after years of silence, it reaches Alpha Centauri. For a few precious minutes, the spacecraft looks back. It gathers images. It measures the environment. It searches for planets. And then it transmits its tiny packet of information toward home. The signal begins its 4-year journey back to Earth. Humanity waits. And somewhere in the darkness between the stars, a machine that began its journey on Earth decades earlier is carrying our first close-up glimpse of another stellar system. That Possibility is what makes the laser sail so compelling. It does not make Alpha Centauri closer. It does something more subtle. It gives us a way to imagine crossing the distance without carrying the entire burden of crossing it on board. And perhaps the first spacecraft to reach another star will not be powerful because it carries an enormous engine. Perhaps it will be powerful because it carries almost nothing at all. Imagine a fuel so energetic that a tiny amount could release more energy than an enormous quantity of conventional rocket propellant. A fuel that does not need to burn, does not need oxygen, does not require a chemical reaction. A fuel in which matter itself becomes part of the energy source. On paper, it sounds almost perfect for interstellar travel. That fuel is antimatter. But antimatter is not a magical substance, and it is not a fuel sitting in some laboratory tank waiting for engineers to put it inside a starship. The reality is much more difficult. Antimatter may represent one of the highest theoretical energy densities available to physics. Yet, producing it, storing it, controlling it, and converting its energy into useful spacecraft motion remain extraordinary challenges. To understand why, we first need to understand what antimatter actually is. Everyday matter is built from particles: electrons, protons, neutrons, atoms, molecules. Everything around us is made from combinations of these particles. But many fundamental particles have corresponding antiparticles. The electron has the positron. The proton has the antiproton. These antiparticles have the same mass as their ordinary counterparts, but opposite electric charge and other corresponding quantum properties. A positron is essentially the antimatter counterpart of an electron. An antiproton is the antimatter counterpart of a proton. And when matter encounters its corresponding antimatter, something remarkable can happen. They can annihilate. The particles disappear as individual matter particles, and their mass is converted into energy carried by other particles and radiation. This is where Einstein's famous equation becomes directly relevant. E mc squared. Mass is a form of energy. The speed of light squared is an enormous number. That means even a tiny amount of mass corresponds to an enormous amount of energy. And antimatter provides a particularly efficient pathway for accessing that energy, because both the matter and antimatter masses can participate in the annihilation. Imagine bringing 1 gram of matter together with 1 gram of antimatter. The total mass involved would be only 2 grams, yet the energy released would be enormous. Using EMC squared, 2 grams of mass corresponds to roughly 1.8 times 10 phi joules of energy. That is about 180 trillion joules. The number is difficult to visualize. And this is why antimatter attracts so much attention from people thinking about interstellar propulsion. Compare it with chemical energy. Chemical reactions involve rearranging atoms and molecules. The energy comes from changes in chemical bonds. Nuclear reactions operate on a vastly greater scale because they involve changes in atomic nuclei. Matter-antimatter annihilation goes even deeper. It converts essentially the entire rest mass involved in the annihilation process into energy carried by other particles. That gives antimatter an extraordinary theoretical energy density. But there is a crucial distinction. Energy density is not the same thing as propulsion efficiency. And propulsion efficiency is not the same thing as technological readiness. This distinction is where many popular descriptions of antimatter go wrong. It is easy to say, antimatter is incredibly energetic, therefore antimatter spacecraft can travel near the speed of light. But physics does not work that simply. First, we have to produce the antimatter, and this is where the dream encounters reality. Antimatter does not naturally accumulate in convenient quantities. We can produce antiparticles in high-energy physics experiments. Particle accelerators can create them. But producing antimatter requires enormous amounts of energy and sophisticated equipment. The process is extremely inefficient. We put substantial energy into a particle accelerator. We collide particles. Some of that energy becomes new particles. Among them may be antiprotons or other antiparticles. Then we have to isolate the antimatter, slow it down, capture it, store it, and prevent it from touching ordinary matter. Every stage loses energy. So while antimatter contains enormous energy when annihilated, the process of manufacturing antimatter currently requires vastly more energy than we can recover from using it. That means antimatter is not an energy source. It is better understood as an energy storage medium. We must first invest energy to create it. Then, theoretically, we could recover some of that energy later through annihilation. This is a fundamental difference. The sun produces energy through nuclear fusion. A nuclear reactor releases energy from nuclear reactions. An antimatter system does not create free energy. It stores energy in an extremely concentrated and extremely difficult form. And right now, we are extraordinarily bad at storing it. Imagine producing a microscopic quantity of antimatter. You cannot simply pour it into a metal tank. The instant it touches the walls, it annihilates. So antimatter must be isolated from ordinary matter. Charged antiparticles can be confined using electromagnetic fields. Particle traps can hold small quantities of antimatter without allowing direct contact with physical surfaces. Scientists have successfully stored antimatter particles for significant periods under controlled laboratory conditions. But the quantities involved are tiny. Not kilograms, not grams, not even anything close to what an interstellar spacecraft would require. The gap between laboratory-scale antimatter and propulsion-scale antimatter is enormous. And that gap may be the greatest obstacle of all. Suppose a future civilization wanted to power an interstellar spacecraft with antimatter. It would need to produce an enormous quantity. That means enormous energy infrastructure, massive particle accelerators, efficient antimatter production, reliable collection systems, long-term storage, and a way to transport the antimatter safely. Every stage would be extraordinarily expensive. And then comes the problem of using it. Antimatter annihilation releases energy in the form of high-energy particles and radiation. That energy does not automatically emerge as a neat beam pointing backward from the spacecraft. It goes where the physics sends it. Some annihilation products are difficult to direct. Some interact strongly with matter. Some penetrate materials. And some carry energy that is extremely difficult to convert into useful thrust. This creates a major propulsion problem. A spacecraft does not simply need energy. It needs directed momentum. Energy must be converted into exhaust moving in a controlled direction. That is what makes a rocket a rocket. Annihilation provides tremendous energy, but engineers still need a mechanism to turn that energy into thrust. One theoretical approach would be to use charged annihilation products and electromagnetic fields to direct them. Another might use annihilation energy to heat a separate propellant. The antimatter would then act more like an extraordinarily powerful ignition source. There are many theoretical possibilities, but none has yet become a practical spacecraft propulsion system. And even if we solve the thrust problem, we face another enemy: heat. Not all of the annihilation energy can become useful forward motion. Some energy will inevitably be deposited in the spacecraft. That energy must go somewhere. A spacecraft cannot simply become hotter forever. In space, heat can primarily be rejected through radiation. But radiators have mass. The faster the spacecraft needs to reject heat, the larger and more capable those radiators must become. And every kilogram of radiator becomes another kilogram the propulsion system must accelerate. Once again, mass creates a vicious cycle. The spacecraft needs more hardware to manage the energy. The additional hardware makes the spacecraft heavier. The heavier spacecraft requires more energy. More energy creates more heat. More heat requires more thermal management. The interstellar propulsion problem returns again and again to the same fundamental constraint: mass, energy, heat, and momentum. Then comes safety. Antimatter is not dangerous because it is radioactive fuel in the conventional sense. The primary danger is annihilation when antimatter encounters ordinary matter. A containment failure could release the stored annihilation energy. For a hypothetical large antimatter supply, that would be an extraordinary hazard. A spacecraft carrying substantial quantities would therefore require multiple independent containment systems. Those systems would need to remain functional during launch, during acceleration, during vibration, during radiation exposure, during decades of operation, and during potential collisions with microscopic particles. The engineering requirements become severe. Now consider the economics. Producing tiny quantities of antimatter today requires sophisticated particle accelerators. The amount produced is minuscule compared with what an interstellar spacecraft would need. The energy cost is enormous. The production process is inefficient. Storage is difficult. And scaling the technology from microscopic laboratory quantities to useful propulsion quantities would require an industrial infrastructure far beyond anything humanity currently possesses. This is why antimatter should not be described as the fuel of the future without qualification. It is better described as one of the most extraordinary theoretical energy reservoirs imaginable. The physics is real. The engineering is not ready. But suppose for a moment that a future civilization solves these problems. Could antimatter propulsion actually accelerate a spacecraft to a significant fraction of light speed? In principle, it could provide an extraordinary amount of energy. And because energy is what ultimately determines how quickly a spacecraft can be accelerated, antimatter could potentially play a role in relativistic propulsion. But there is another wall: special relativity. As the spacecraft's velocity approaches the speed of light, the energy required to continue increasing its velocity rises dramatically. At low velocities, adding energy can produce substantial increases in speed. At relativistic velocities, every additional fraction of light speed becomes increasingly expensive. Going from 10% of light speed to 20% is difficult. Going from 50% to 60% is much harder. Going from 90% to 99% is vastly harder still. And reaching exactly the speed of light is impossible for an object with non-zero rest mass under our current physical theories. So, even the most powerful conceivable fuel does not provide a shortcut through relativity. Antimatter does not make the speed of light irrelevant. It simply gives us an extraordinarily concentrated source of energy with which we can confront the problem. And there is another subtle point. If the spacecraft is traveling extremely fast, its kinetic energy becomes enormous. For a spacecraft with mass m, the classical equation, E1/2 mv², eventually becomes insufficient. At relativistic speeds, we must use Einstein's relativistic energy equations. The spacecraft's total energy rises dramatically as its velocity approaches c, the speed of light. This means that an interstellar antimatter spacecraft would eventually encounter diminishing returns. More antimatter produces more energy. More energy produces more velocity. But each additional increase in velocity becomes harder and harder to obtain. The universe does not give us a simple linear relationship between fuel and speed. It gives us a curve, and that curve becomes brutally steep near light speed. So could antimatter take us to 20% of light speed? In principle, an antimatter-based propulsion system could potentially provide enough energy density to make such velocities part of serious theoretical discussions. Could it take us to 50%? Perhaps with an extraordinarily advanced system. Could it take us to 90%? The energy requirements become enormous. Could it reach 99.9%? The requirements become almost unimaginable. And none of these statements mean that such spacecraft are technologically feasible today. That distinction must remain clear. High energy density does not equal ready-made propulsion technology. Antimatter gives us something physics values enormously. A way to concentrate tremendous energy into a tiny amount of mass. But an interstellar engine needs more than energy. It needs controlled energy, directed momentum, thermal management, storage, reliability, navigation, shielding, and a way to decelerate at the destination. In other words, antimatter solves one part of the problem, while creating a collection of new ones. And perhaps the most fascinating issue is that we do not yet know whether antimatter should be the primary propulsion fuel at all. A future spacecraft might use antimatter in combination with another system. It could serve as an ignition mechanism for fusion. It could help trigger reactions that are otherwise difficult to initiate. It could provide a compact source of energy for an electric propulsion system. Or perhaps an entirely different technology will make antimatter unnecessary. This is what makes the subject so interesting. We are not looking at a finished technology. We are looking at a boundary between known physics and future engineering. The laws of physics tell us that matter-antimatter annihilation is real. They tell us that mass can become energy. They tell us that enormous energy densities are possible. But they do not tell us that humanity can cheaply manufacture, safely store, and efficiently direct that energy into an interstellar spacecraft. That is our problem. And it is a very large one, because somewhere beyond the solar system, Alpha Centauri remains 4.37 light-years away. The distance has not changed. Chemical rockets make the journey thousands of years long. Ion engines improve efficiency, but remain too slow. Nuclear propulsion could potentially shorten the journey dramatically. Laser sails could avoid carrying the primary energy source on board, and antimatter offers perhaps the most concentrated energy reservoir of them all. But every approach eventually confronts the same fundamental reality. The universe allows us to move. It does not make moving fast easy. And it certainly does not make moving near light speed cheap. Perhaps the future of interstellar travel will not depend on discovering one magical fuel. Perhaps it will depend on combining several technologies: nuclear energy, advanced electric propulsion, laser systems, ultralight spacecraft, and perhaps, one day, controlled antimatter. The first starship may not be powered by a single, revolutionary invention. It may be the result of hundreds of smaller breakthroughs finally working together. And if that day comes, the ultimate limitation may no longer be whether we can generate enough energy. It may be whether we can control enough energy without destroying the machine designed to carry it. Because at the edge of light speed, the challenge is no longer simply building a stronger engine. It is learning how to survive the energy required to make the universe's vast distances feel slightly smaller. What if the problem is not that we cannot build a spacecraft fast enough? What if the real problem is that human beings simply do not live long enough? Imagine launching a spacecraft toward Alpha Centauri. The engines work perfectly. The navigation is flawless. The life support systems function exactly as designed. But the journey takes 200 years. The people who launch the spacecraft will never see the destination. Neither will their children. Perhaps not even their grandchildren. The spacecraft would become something very different from every space mission humanity has ever attempted. It would no longer be a vehicle carrying passengers from one place to another. It would become a world. A sealed environment traveling through interstellar space. A place where children could be born, grow up, work, fall in love, raise families, grow old, and die without ever setting foot on Earth. This is the basic idea behind a generation ship. A spacecraft designed not for a single human lifetime, but for multiple generations. The first generation launches. The second is born during the journey. The third grows up knowing Earth only through stories, recordings, photographs, and historical archives. The fourth may eventually become the generation that reaches another star. The destination is no longer a place the original crew is traveling toward. It becomes a destination inherited by their descendants, and that changes the meaning of space exploration completely. Because a generation ship would not simply be an engineering project. It would be a civilization in miniature. Imagine standing inside such a vessel. Outside the hull is almost absolute darkness. There is no atmosphere, no breathable air, no natural ecosystem, no convenient rescue, no nearby planet. The nearest stars are separated by trillions of kilometers. Inside the spacecraft, however, life must continue. Plants must grow. Water must circulate. Waste must be recycled. Oxygen must be regenerated. Food must be produced. Children must be educated. Machines must be repaired. Knowledge must be preserved. And somehow, society must remain stable. The spacecraft would need to function as a closed ecological system for decades, centuries, or perhaps millennia. That is an extraordinary requirement. On Earth, ecosystems are supported by a vast planetary environment. The oceans regulate climate. The atmosphere provides gases. The biosphere cycles nutrients. The sun provides an almost limitless source of energy. A generation ship would have none of those luxuries. Every kilogram of water would matter. Every kilogram of food would matter. Every molecule of oxygen would matter. A closed-loop system would have to recycle almost everything. Waste would not simply be discarded. It would become part of another process. Water would be purified and reused. Carbon dioxide would be removed from the atmosphere and converted back into useful biological material. Organic waste could become fertilizer. Plants could provide food and help regulate the atmosphere. Animals might become part of the ecosystem. The ship would effectively need to become an artificial biosphere. And we have already learned how difficult that can be. Experiments such as Biosphere 2 demonstrated how challenging it is to create a stable, mostly closed ecological environment even on Earth. Small imbalances can become enormous problems. Oxygen levels can change. Carbon dioxide can accumulate. Microorganisms can behave unpredictably. Plants can fail. Chemical cycles can become unstable. Now imagine attempting something similar inside a spacecraft, millions of times farther from Earth than any ordinary mission, and then imagine maintaining it for several centuries. The engineering challenge becomes staggering, but the environment outside the ship is equally dangerous. One of the greatest threats is radiation. Earth has an enormous advantage. Our atmosphere provides protection. Our planet's magnetic field helps deflect charged particles. A deep space spacecraft does not have that protection. Galactic cosmic rays can pass through space at enormous energies. Solar particle events can produce dangerous radiation bursts. For a short robotic mission, radiation is already a concern. For humans living aboard a spacecraft for generations, it becomes one of the central design problems. A generation ship would require substantial shielding. Water could potentially be used as part of that protection. Other materials could be placed around living spaces. Some designs might use layers of hydrogen-rich materials because they can be effective against certain forms of radiation. But shielding has a cost. More shielding means more mass. More mass means more energy required to accelerate the spacecraft. Again, the same problem returns. Mass is expensive, and then there is gravity. Humans evolved on Earth under the influence of 1G, our bones, muscles, cardiovascular system, balance mechanisms. Even the development of our bodies are adapted to Earth's gravity. Long-duration exposure to microgravity causes serious physiological changes. Astronauts lose bone density. Muscles weaken. Fluids shift toward the upper body. Vision can be affected. The cardiovascular system changes. A journey lasting several centuries cannot simply assume that humans will remain healthy in weightlessness. So, a generation ship may need artificial gravity. One possibility is rotation. Imagine a massive, cylindrical, or ring-shaped spacecraft spinning continuously. The rotation would create an apparent outward force for people inside. Walk toward the outer edge, and you would experience something resembling gravity. The ship could contain habitats arranged around the rotating structure, agricultural areas, living quarters, workspaces, schools, medical facilities, perhaps entire communities. From inside, the spacecraft might not feel like a vehicle at all. It could feel like a small world. There could be streets, gardens, artificial skies, day-night cycles. The inhabitants might eventually stop thinking of themselves as passengers. They would simply think of the ship as home. And that creates a profound psychological problem. What happens to a population that grows up knowing they will never see Earth? The first generation would remember the planet. They would have photographs. They would remember oceans, mountains, cities, rain, sunlight, open skies. But their children might never experience any of those things directly. For the second generation, Earth becomes history. For the third, perhaps mythology. The ship itself becomes their world. This raises questions that engineers cannot solve with equations. Who controls the ship? Who decides its destination? Who has the authority to change the mission? What happens if future generations no longer want to go to Alpha Centauri? The original crew might consider the destination sacred. Their descendants might disagree. A child born on the ship never consented to the mission. They inherited it. That creates an ethical problem unlike anything in conventional exploration. A generation ship would effectively impose the consequences of decisions made centuries earlier upon people who had no role in making them. Society would therefore become one of the spacecraft's most important systems. There would need to be rules, education, government, medical care, conflict resolution, resource allocation, reproductive policies, and perhaps most importantly, a shared reason for continuing. Because boredom alone could become dangerous. A journey lasting centuries cannot rely on entertainment as a psychological solution. People would need purpose. They would need meaningful work, relationships, culture, art, science, religion, or philosophy, depending on the society. The ship would need more than oxygen and food. It would need a civilization, and that civilization could evolve. Languages could change. Traditions could develop. New music could appear. New political systems could emerge. The descendants of the original crew might eventually create customs that would be completely unfamiliar to the people who launched the ship. At some point, the mission could stop being a project controlled by Earth. It could become an independent human society. And perhaps that is the most fascinating possibility. A generation ship would not merely transport humanity to another star. It could create a new branch of humanity. But there is another concept that often appears in discussions of long-duration interstellar travel: hibernation. What if humans did not remain conscious for the entire journey? What if biological activity could be dramatically slowed? Animals in nature already demonstrate forms of metabolic suppression. Certain organisms can survive extraordinary environmental conditions by reducing their biological activity. Scientists have studied suspended animation and metabolic slowing in various contexts. Science fiction has transformed this into cryogenic sleep. A crew enters a chamber. Their metabolism slows. The spacecraft travels for decades. They awaken near the destination. It sounds attractive. If humans could safely enter a long-duration suspended state, the psychological and resource problems could potentially be reduced. There would be fewer active people consuming food, less social conflict, less boredom, less aging. The spacecraft might not need to support an entire living population throughout the journey. But there is an enormous gap between theoretical research and a human system capable of safely suspending people for decades. We do not currently possess a proven technology that allows humans to enter reversible suspended animation for interstellar travel. And even if we did, we would still need to solve radiation, hardware reliability, power, life support, awakening, medical complications. And what happens if the system fails? The same problem appears again. A starship cannot depend on a technology that works only under ideal conditions for a few months. It must work for decades or centuries. This is where robotic probes have a major advantage. A robot does not need food. It does not need oxygen. It does not need artificial gravity. It does not need schools. It does not need political institutions. It does not need to reproduce. And if a robotic spacecraft takes 50 years to reach Alpha Centauri, the machine does not care. It can simply continue operating. This is why the first interstellar explorers are much more likely to be robotic than human. A tiny probe accelerated by a laser sail could potentially cross the distance in decades. A generation ship could take centuries. A human mission using conventional propulsion could take far longer. Each approach represents a different philosophy. Robotic exploration minimizes biological requirements. Generation ships accept the biological problem and turn the spacecraft into a society. Hibernation attempts to reduce the biological problem by putting humans into a dormant state. And perhaps future technology will combine elements of all three. But there is something important hidden beneath these possibilities. An interstellar mission may not be a single mission at all. It may be a project that belongs to an entire civilization. Think about the timescale. A spacecraft could take decades to reach its destination. The people who design the propulsion system may never see the launch. The people who launch it may never see the arrival. The scientists who interpret its first data may be several generations removed from the original engineers. That means an interstellar civilization would have to learn how to build projects that outlive individuals. Institutions would need to survive. Knowledge would need to be preserved. Technical standards would need to remain understandable. The mission would become a chain of responsibility stretching across generations. One generation builds the engine. Another maintains the spacecraft. Another operates it. Another receives the data. Another perhaps builds the next spacecraft. And eventually, another generation might become the first to physically stand beneath another star. That is why Alpha Centauri represents something larger than a destination. It is a test of whether a technological civilization can think beyond individual lifetimes. We are accustomed to projects that produce results within years, sometimes decades. Interstellar travel may demand centuries, perhaps millennia. The first generation may never see the result of its work, and yet it may still decide to begin. That is a very different definition of exploration. The ancient builders of monumental structures Sometimes created work was intended to outlast their own lives. But an interstellar spacecraft could require something even more demanding. Not simply constructing a monument, but maintaining a functioning civilization inside a machine while it travels through the darkness between stars. And eventually, if the spacecraft succeeds, someone may look through a window and see another sun rising. Not Earth's sun, not a familiar star, but Alpha Centauri. For that person, Earth may be nothing more than an ancient memory preserved in archives, a place their ancestors once called home. The people who launched the spacecraft would be long gone. Their grandchildren would be gone. Their great-grandchildren perhaps forgotten. But the mission would still be alive. And that may be the most profound possibility of all. The first human journey to another star may not belong to one astronaut. It may not belong to one crew. It may not even belong to one generation. It could belong to hundreds of generations working together across time. Because if we cannot yet make humanity fast enough to cross the stars, perhaps the only solution is to make humanity patient enough to wait for the journey to finish. And when the descendants finally arrive, they may discover something extraordinary. The hardest part of reaching another star was never simply crossing the distance. It was becoming the kind of civilization capable of crossing it. Imagine the moment a spacecraft finally reaches Alpha Centauri. After decades of travel, the tiny machine arrives at another star system. Its instruments activate. Its cameras begin recording. Perhaps it sees a planet. Perhaps it detects an atmosphere. Perhaps it discovers something completely unexpected. The spacecraft has completed the journey. But there is one enormous problem. Nobody on Earth knows what it has found yet. Because reaching another star and communicating with Earth are two completely different problems. The spacecraft can arrive. The data still has to come home. And that changes the meaning of an interstellar mission. We often ask, how long would it take to reach Alpha Centauri? But perhaps the more important question is, who will still be alive when the first message arrives? The distance between Earth and Alpha Centauri is approximately 437 light-years. That means light itself needs about 4.37 years to cross the gap. No radio signal can arrive faster. No conventional laser communication beam can arrive faster. Information cannot simply skip across the distance. So even if a spacecraft somehow reached Alpha Centauri instantly, the first message telling Earth about its arrival would still require approximately 4 years and 4 months to reach us. And if Earth sends a question back, another 4.37 years would pass before the spacecraft could receive the response. A simple question and answer exchange would therefore require approximately 74 years, 8 years, almost 9. For a civilization accustomed to instant communication, that delay is enormous. Imagine sending a message to another planet and waiting years to find out whether anyone received it. Now make the spacecraft itself slower. Suppose a future laser sail probe travels at 20% of the speed of light. The simple travel time to Alpha Centauri is approximately 22 years. 22 years just to arrive. Then the spacecraft collects its data. It processes the information. It prepares the transmission. And the signal begins the return journey. Another 4.37 years. The earliest scientific data could therefore reach Earth roughly 26 years after launch, even under an extremely optimistic scenario. 26 years. A child could be born on the day the spacecraft launches, grow into adulthood, and receive the first images from another star before turning 30. That sounds like a human-scale mission. But consider what happens if the spacecraft is slower. Suppose the journey takes 50 years. The spacecraft arrives. The data requires another 37 years to reach Earth. The first meaningful scientific results arrive more than 54 years after launch. The engineers who designed the mission may already be retired. Some may have died. The scientists who calculated the trajectory may no longer be alive. The person who presses the launch command may never see the images. And the people receiving the information could belong to an entirely different generation. Now extend the journey to a century. The spacecraft travels for 100 years. Then the signal travels for another 437. The mission has crossed a century. The people who launched it are almost certainly gone. Their children may be gone. Their grandchildren may be elderly. The civilization receiving the data may have completely different technology, politics, languages, and priorities. The spacecraft would be sending its message into a future world. And that is where interstellar communication becomes something much deeper than an engineering problem. It becomes a problem of civilizational time. We normally think of communication as an exchange between people who exist at roughly the same moment. You speak, someone listens. You ask, someone answers. Interstellar communication breaks that assumption. The sender and receiver may belong to different generations, perhaps radically different generations. The spacecraft itself becomes a kind of time capsule, a message created by one civilization, received by another version of the same civilization decades later. And if the journey takes centuries, the distinction becomes even more profound. Imagine a spacecraft launched in the year 2100. It reaches Alpha Centauri in the year 2300. Its message arrives on Earth in 2304. Who receives it? The people who designed the spacecraft? No, their descendants. The political institutions that funded the mission may no longer exist. The company that built the spacecraft may be a historical footnote. The language used by the engineers may have changed. The original mission objectives might seem strange to the people living in 2304, and yet the spacecraft would still be carrying their ancestors' questions. That is the strange power of robotic exploration. A robot does not care how long the journey takes. It does not become impatient. It does not age in the biological sense. It does not need to understand why its mission matters. It simply follows its programming. A tiny spacecraft could travel for decades through interstellar darkness, and then wake its instruments when it reaches the target. It could take photographs, measure magnetic fields, analyze particles, search for atmospheric signatures, study a planet, then transmit the information home. The machine may have no idea who will eventually receive the message. And perhaps that does not matter, because the mission was never truly about communicating with the people who launched it. It was about creating information that could survive long enough to reach someone. This is one reason the design of an interstellar probe must include not only propulsion, but long-term communication. The spacecraft needs a way to generate data, store it, compress it, prioritize it, transmit it, and aim the signal toward Earth. All of this must happen across more than 4 light years. The signal weakens with distance. The spacecraft has limited power. Its antenna may be extremely small, and the Earth itself is moving. The spacecraft is moving. Alpha Centauri is moving. The solar system is moving through the galaxy. The target will not occupy exactly the same position decades later that it does today. Navigation and communication therefore become intertwined. A probe must know where it is. It must know approximately where Earth will be. And it must point its communication system in the correct direction. For a tiny spacecraft, this is extraordinarily difficult. Imagine holding a flashlight in a dark field and trying to illuminate a target several trillion kilometers away. Now imagine that both you and the target are moving. Now shrink the flashlight to the size of a postage stamp. That is the kind of problem an interstellar communication system faces. Laser communication may offer advantages because laser beams can be extremely narrow and can carry enormous amounts of information. But narrow beams create another problem. The spacecraft must point them extremely accurately. A tiny angular error can cause the beam to miss Earth completely. Radio communication has been used successfully across the solar system for decades, but interstellar distances make the signal budget much more severe. The receiving infrastructure on Earth would need extraordinary sensitivity. Large antenna arrays, advanced signal processing, extremely precise timing, and perhaps multiple receiving stations distributed around the planet. The spacecraft may also need to transmit data slowly. Instead of sending a high-resolution image in seconds, it could take hours or days to transmit a single scientifically important dataset. This means mission designers would have to decide what matters most. A few spectacular photographs? A detailed atmospheric spectrum? Magnetic field measurements? Particle data? Images of planets? The spacecraft cannot send everything. It has limited energy, limited storage, limited communication bandwidth. Every transmitted bit must be chosen carefully. And then comes the most unsettling possibility. What if nobody is listening? Imagine a probe launched toward Alpha Centauri on a mission lasting 500 years. The spacecraft reaches the destination. It transmits its message. The signal takes another 4.37 years to reach Earth, but the civilization that launched the spacecraft has changed beyond recognition. Maybe humanity has survived and evolved. Maybe our descendants have moved beyond Earth. Maybe the original communication network no longer exists. Maybe the languages have changed. Maybe the mission itself has been forgotten. The spacecraft could be broadcasting into a civilization that no longer remembers why it was sent. That possibility makes interstellar exploration strangely similar to archaeology. We could be sending artifacts into the future. A spacecraft becomes a physical record of a civilization at a particular moment in history. Its instruments capture a distant star. Its memory stores measurements. Its transmitter sends those measurements home. And hundreds of years later, someone may discover the signal and reconstruct what our civilization once wanted to know. The spacecraft becomes a message across time. This is particularly important if humans eventually attempt missions lasting thousands of years. At that point, the phrase mission control begins to lose its familiar meaning. Who is mission control after 1,000 years? The original organization is gone. The original engineers are gone. The original governments may be gone. The original civilization may be transformed. The spacecraft may outlive the institutions that created it. And yet the machine continues. That means an interstellar mission must be designed with a kind of technological independence. It cannot rely on a single computer center on Earth remaining operational forever. It cannot assume one particular communications protocol will always be understood. It may need to carry extensive documentation, self-describing data formats, redundant communication methods, autonomous fault recovery, perhaps even instructions explaining how to interpret its own scientific measurements. The probe would need to be able to say, in effect, "This is what I measured. This is how I measured it. This is what these numbers mean." Because the person reading the data may have been born decades or centuries after the spacecraft was launched. This changes the way we think about exploration. A traditional expedition begins and ends within the lifetime of its participants. An interstellar mission may not. The people who design it may be one generation. The people who launch it may be another. The people who receive its first signal may belong to another. And the people who finally understand the full scientific significance of the mission may come later still. The mission becomes a chain connecting generations, and perhaps that is exactly what makes it so powerful. We tend to imagine the first message from another star as a dramatic moment. A screen lights up, a photograph appears, people cheer, but the real story may be quieter. Someone, decades from now, sits in front of a computer. A faint signal arrives. A packet of data is reconstructed. An image slowly emerges, and that person realizes, "This machine was launched before I was born. Perhaps before my parents were born. Perhaps before my grandparents were born. The people who built it will never see this image, but they made it possible." That is what interstellar exploration ultimately asks of a civilization. Not simply, can we build a spacecraft fast enough? But, can we build something that survives long enough for its message to matter? Because the first interstellar spacecraft may cross the distance between stars in 20 years, but the civilization that receives its final signal may be separated from its creators by an even greater distance. A distance measured not in kilometers, not in light years, but in generations. And perhaps this is the deepest question hidden behind the journey to Alpha Centauri. We think we are sending a spacecraft to another star, but maybe we are actually sending a message to a future version of ourselves. A message that says, "We were here, we looked outward, we knew the stars were far away, and we decided to begin anyway." The spacecraft may arrive decades from now. The signal may arrive several years after that. And the person who finally sees it may never have met anyone involved in the mission. Yet for a few seconds, across 437 light years of darkness, the past and future will touch. And that may be the first true conversation humanity ever has with another star. Return to the number we began with, 4.37 light years. At the beginning of this journey, it sounded like a distance. A number, a measurement between two stars. More than 40 trillion kilometers separating our solar system from our nearest stellar neighbor. But after everything we have explored, that number means something very different. Because 4 37 light-years is not really a measurement of space anymore. It is a measurement of time, a measurement of energy, a measurement of technology, and perhaps, more than anything else, a measurement of civilization. We began by asking a simple question: how long would it take to reach Alpha Centauri? The answer depended on how fast we could travel. Chemical rockets could make the journey extraordinarily long. Ion propulsion could improve efficiency, but not eliminate the enormous distance. Nuclear propulsion could potentially take us much farther and much faster. Sails could theoretically push tiny spacecraft toward a significant fraction of light speed. Antimatter could provide an extraordinary energy density if humanity ever learns how to produce and control it at useful scales. And generation ships could abandon the idea of completing the journey within a single human lifetime altogether. Each technology represents a different answer to the same problem. But there is something deeper hiding underneath all of them. The question is not simply, how do we build a faster spacecraft? It is, what kind of civilization can build something that takes decades or centuries to complete its mission? That is a much harder question. Chemical propulsion represents where we are now. It is the technology that carried humans beyond Earth. It helped place spacecraft on trajectories toward the planets. It sent probes toward the edge of the heliosphere. It is powerful, reliable, and extraordinarily well understood. But chemical propulsion is fundamentally constrained by the amount of energy available from chemical reactions. For the stars, that energy density is simply too low. The rocket can fly. It just cannot fly far enough, fast enough. Ion propulsion represents a different philosophy. Instead of producing enormous thrust for a short period, it produces tiny thrust for a very long time. It sacrifices force for efficiency. That makes it extremely useful for deep space missions. But Alpha Centauri exposes its limits. A spacecraft can push itself gently for years and still require centuries or millennia to cross the gap. Then comes nuclear propulsion. Here, the energy density changes dramatically. Nuclear reactions can release vastly more energy than chemical reactions. Nuclear, thermal propulsion could potentially produce higher exhaust velocities. Nuclear electric propulsion could provide continuous power for efficient electric engines. More advanced concepts could potentially use nuclear pulse propulsion or fusion. Suddenly, interstellar travel begins to move from impossible-looking engineering toward extremely difficult engineering. But there is still a gap, a very large one. That gap is where concepts such as the laser sail become interesting. A laser sail does not try to carry all of its propulsion energy. The spacecraft carries the sail. The laser remains behind. Photons push the sail forward, and because the spacecraft can be incredibly small, the energy required to accelerate it becomes far more manageable. A gram-scale probe, traveling at around 20% of the speed of light, could, in principle, cross the distance to Alpha Centauri in roughly 22 years, ignoring the full complexity of acceleration, navigation, and the encounter. That is remarkable. But it also reveals something important. The first spacecraft to reach another star may not be a giant starship. It may be microscopic, a tiny machine, a few grams of electronics, a thin reflective sail, a camera, a sensor, a communication system. Nothing about it, would resemble the enormous starships of science fiction. And perhaps that is exactly why it could be our first realistic step. We do not need to solve every problem of human interstellar travel at once. We may only need to solve the problem of sending a tiny machine, then another, then another. Each mission could teach us something. How does material behave at relativistic speeds? How much damage does interstellar dust cause? How accurately can a laser sail be aimed? How do we communicate across several light years? How do we protect miniature electronics? How do we navigate another star system? The first interstellar probes could become experiments for the civilization that eventually builds larger spacecraft. And somewhere beyond that lies antimatter. Antimatter represents something almost philosophical. It reminds us that the universe contains energy densities vastly beyond chemical reactions. Matter and antimatter can annihilate. Mass can become energy. The potential is extraordinary, but so are the difficulties. We currently produce only tiny quantities. The process is inefficient. Storage is extremely difficult. The energy released must be controlled. Heat must be managed. Momentum must be directed. And the closer a spacecraft approaches light speed, the more brutally relativity responds. Antimatter does not eliminate the laws of physics. It simply gives us a more powerful tool with which to confront them. And then there is perhaps the most radical idea of all. The generation ship. Instead of making the spacecraft fast enough for one human lifetime, make the mission long enough for many generations. The first crew launches. Their children are born aboard the ship. Their grandchildren grow up there. Their descendants eventually reach Alpha Centauri. At that point, the spacecraft is no longer simply a vehicle. It is a civilization. It has schools, agriculture, government, culture, art, science, families, history. Perhaps even religions and philosophies that never existed on Earth. The people who finally arrive may have no personal memory of Earth. Earth could become something their ancestors described. A distant blue world. A place that existed before their own society was born. And that possibility forces us to rethink the meaning of exploration. The first humans to walk on another world did so within their own lifetime. The first humans to reach another star might not. The people who begin the mission may never see the destination. They may never hear the final transmission. They may never know whether the spacecraft succeeded. And yet they may choose to begin anyway. That is a completely different form of exploration. It requires a civilization capable of thinking beyond individual lifetimes, beyond elections, beyond economic cycles, beyond corporate schedules, beyond the lifespan of individual institutions. It requires memory. A civilization must be able to preserve knowledge across generations. It must maintain scientific understanding. It must maintain infrastructure. It must maintain the will to continue. Because an interstellar project can fail, not only because an engine breaks, but because the civilization behind the engine disappears. Imagine launching a spacecraft in the year 2100. Suppose it takes 100 years to arrive. The spacecraft reaches Alpha Centauri in 2200. Its signal reaches Earth several years later. Who receives it? Not the engineers. Not the original mission controllers. Not the people who watched the launch. Their descendants. And if the mission takes 500 years, the gap becomes even larger. The people who receive the data may live in a civilization almost impossible for us to imagine. They may use technologies we have never invented. They may have different languages, different political systems, different values. Perhaps they will look back at the original spacecraft as we look at ancient monuments, an artifact from an earlier age, and yet that artifact will still carry information. It will say, someone hundreds of years ago wanted to know what was there. Someone believed the question was worth asking. Someone built a machine and sent it into the darkness. That may be one of the most powerful things about exploration. It allows one generation to ask questions that another generation eventually answers, and Alpha Centauri may become the ultimate expression of that principle. The distance between the stars is enormous, but the distance between generations can also be enormous. The spacecraft must cross one. The civilizations must cross the other. And perhaps both journeys are equally important. Because building an interstellar spacecraft requires more than propulsion. It requires energy. It requires materials. It requires computing. It requires communication. It requires navigation. It requires scientific knowledge. But above all, it requires continuity. A civilization that cannot preserve knowledge for a century may struggle to operate a century-long mission. A civilization that cannot maintain institutions across generations may struggle to maintain a generation ship. A civilization that cannot plan beyond the next decade may never build a project whose greatest results arrive after its founders are gone. This is why Alpha Centauri may represent more than the nearest neighboring star. It may represent a test of civilization itself. Can we build something that outlives us? Can we invest in a result we will never personally experience? Can we preserve knowledge for people we will never meet? Can we create a machine and trust future generations to finish what we started? Those questions sound philosophical, but they are also engineering questions. A spacecraft that travels for decades requires a civilization capable of maintaining it for decades. A spacecraft that travels for centuries requires something even more difficult. It requires a civilization capable of remembering why the spacecraft exists. And perhaps that is why the first interstellar mission will be so important. Not simply because a spacecraft reaches another star, but because the mission itself will demonstrate that humanity can coordinate its efforts across time. The first signal from Alpha Centauri may therefore be more than a scientific discovery. It could become a message from our own past. Imagine that moment. A signal arrives. A telescope or receiver confirms it. The data is reconstructed. An image appears. For the first time, humanity sees something from another star system through a machine we built. The people watching may not be the people who launched it. They may be the children, the grandchildren, or the distant descendants of those people. Perhaps they will stand together beneath the night sky, and somewhere in that sky will be the faint point of light that received our machine. They will know that decades earlier, someone on Earth looked at that same star and asked, "Can we reach it?" And someone else answered, "Let's try." That is what the journey to Alpha Centauri ultimately represents. Not merely distance, not merely speed, not merely propulsion. It represents time. It represents energy. It represents memory. And it represents the ability of a civilization to survive long enough to complete what it begins. The universe does not appear to be in a hurry. Stars burn for billions of years. Planets orbit for billions. Galaxies evolve across unimaginable timescales. Human beings live for decades. That mismatch may be our greatest obstacle, but perhaps it is also our greatest opportunity. Because if humanity learns to think beyond a single lifetime, if we learn to build machines that outlive their creators, if we learn to preserve knowledge across generations, then the stars may stop being destinations belonging only to the future. They could become projects belonging to the present. A spacecraft launched today might not arrive today. It might not arrive tomorrow. It might not arrive during the lifetime of the person who designed it. But that does not make the journey meaningless. Quite the opposite. It means the journey connects people who may never meet. A scientist in one century begins the mission. An engineer in another maintains the technology. A descendant in another receives the signal. And somewhere in between, a tiny machine crosses the darkness. The spacecraft is only the messenger. The real journey is being made by the civilization behind it. And perhaps one day, humanity will finally send that first true interstellar probe toward Alpha Centauri. Earth will become smaller behind it. The moon will disappear into the darkness. The planets will become points of light. The sun itself will gradually become another star, and eventually, the spacecraft will look back. Our entire world will be somewhere behind it. A tiny planet, a small blue point, surrounded by darkness. And ahead, another star, another system, another possible beginning. The distance between them will still be 4.37 light-years. Physics will not have changed. The universe will not have become smaller. We will simply have become capable of crossing a little more of it. And that leaves us with one final question. Not a question about rockets. Not about lasers. Not about antimatter. A question about us. If you could launch a spacecraft toward Alpha Centauri today, knowing with absolute certainty that you would never live to see it arrive, would you still launch it? Because perhaps the first step toward another star is not building a faster engine. Perhaps it is deciding that a future we will never see is still worth building.